Hello, welcome back. The title of this lesson is called Combination, Decomposition, and Combustion Reactions. This is part 1. So, as you might guess from the title, we're going to learn about classifying chemical reactions into different types, essentially. Now, these 3 types that we're going to learn about today, they're not the only types of chemical reactions, but they do form very broad classes that we see over and over and over again. So in the last couple of lessons, we learned how to write down chemical reactions. We learned how to balance them and why we need to balance chemical reactions. Here, we're going to learn about different examples of combination reactions, decomposition reactions, and combustion reactions. And so we'll just go through and write them down and give several examples of each. And along the way, we will also be balancing some of these. So we'll get a little bit of reinforcement practice of balancing chemical equations as we've done in the last lesson. So let's take a look at the first type here. The first broad category, we call it a combination reaction. Right? So combination reactions can take many different general flavors to it, essentially. But if you look at the big picture in general, it's like if you have some chemical compound or species, call it A, and you add that or combine it with or react it with some other chemical species B, then what you get is a new chemical species C. Now this is just a cartoon reaction. It's not a real reaction, but some reactant combines or reacts with another reactant, and what you get is a one and only one product. You say that they combine together to form some product, okay? That's why it's called a combination reaction, right? So let's take a look at some simple examples of these. Some of these will be a little simpler and some of them will be a little more involved. So let's take a look at taking carbon as a solid and adding it to oxygen. Remember, oxygen is diatomic, so when we write oxygen, we write it as O2, and that would be in the gas phase. And if you combine these and react these together, then what you actually find out that you get is CO2, carbon dioxide, which is also a gas. All right? So before we go any farther, let's just see if this makes sense, if this chemical reaction happens to be balanced. So let's take a look. You have carbon. Remember, carbon's all around us. Carbon, you can have pure carbon, of course, and you can have other compounds with carbon in them. But in this case, we're just taking pure carbon and combining it with oxygen. So one carbon, there's one carbon over here, 2 oxygens, and there's 2 oxygens over here. So this reaction is already balanced. There's nothing to do. So just to remind you of that, we can just put, BAL or something over in the margin over there, just to remind you that this is essentially already balanced. Now this is a combination reaction because you have 2 different reactants that come together, right? And they combine to form a single product. You can see the carbon that was present before is in the product, and the oxygen that was present initially is also in the product. They have combined together to form a more complex molecule, CO2, carbon dioxide, but initially they come together and they combine together. So combination reaction. Now I'm going to take this opportunity to point out that we're going to learn about decomposition reactions. We're also going to learn about combustion reactions. This also happens to be a combustion reaction. All right, so some of these classifications can have some overlap. So this is a combination reaction because we form a single product and they're combining together, but it's combining with oxygen, usually in the presence of a flame, and also heat and light is what comes out of this as well, usually. And so it's also a combustion reaction. So we'll talk about and kind of hold that in the back of our mind when we talk about combustion reactions in a second. Just know that reactions can have multiple labels. This is a combustion reaction, also a combination reaction. So it doesn't have to be one classification. It can satisfy multiple different labels. All right? So we'll give one more example of this type, and then we'll move on to decomposition reaction. Let's take a look at the reaction of magnesium as a solid. Combine that with oxygen, which is a gas, again, O2. And what do we get? MgO as a solid. Now, is this a combination reaction? Yes, it is, because you have a reactant and another reactant. They come together and they form a single product. They combine and you'll have one and only one product, which is the combination of the 2 reactants. Now, also, this is a combustion reaction as well, right? Because you're adding oxygen. And, when you actually do this, you'll find out that there's heat and light and a flame. And so this is also a combustion reaction. So it's not always the case that combination reactions are also combustion reactions, but when you are combining with oxygen and heat and light and flame are involved, it's also a combustion reaction. So this, again, satisfies both labels. Now, is this balanced? We have one magnesium, two oxygens, and only one oxygen. So this is not a balanced reaction. So we can get some practice with balancing it, and it's a fairly simple reaction. So how do we balance it? Again, we start over, one magnesium, two oxygens, and only one here. So I need to balance the oxygen atoms by putting a coefficient of 2 in front. And when I do that, of course, now I have two magnesiums over here and only one over here. So in order to balance that, I rewrite it again, Mg, and then we have O2 yields 2 MgO, magnesium oxide there. And so now I have one magnesium and two over here, so I balance it by putting a 2 in front. So let's check. Two magnesiums, two oxygens. This is the balanced chemical reaction. Now, to be totally proper, and I think probably the best answer, you would again write the state of matter in, that this is a solid, that the oxygen was a gas, and that the product here was a solid. So the answer being 2 Mg plus O2 yields 2 MgO. This is a combination reaction, also a combustion reaction. We'll talk about those a little later. So this class of reaction was in general taking two either elements, compounds, just two species, two reactants, combining them together to form a single product. Now, the next class is called a decomposition reaction. It's the exact opposite of this. So instead of two things coming together to form a product, we start with something complex and it decomposes into simpler pieces. That's what a decomposition reaction is. So I want to write down the next class here, which is called decomposition reaction. Right? And I'll underline this guy. So if a combination reaction is A plus B giving a single product C, then a decomposition reaction is if you start with the single product C and then it reacts and decomposes into two products A and B. So you start with something more complex and it breaks down into constituent parts, into something simpler here. So decomposing means it breaks apart, whereas combination means it comes together. All right? So let's take an example of this. Let's take a look at lead carbonate, so PbCO3. This is the carbonate ion, so lead carbonate, and that's a solid. And let's say that it reacts in such a way that it breaks down into lead oxide, which is a solid, plus CO2, which is a gas. So first of all, does this look like a decomposition reaction? Well, you start with something complex, and you could just see that if you could break these things apart, of course it doesn't break in exactly in half, where the lead is by itself and the carbonate is by itself. I mean, that could happen, but usually it's a little more complex than that. But you can see that this thing does break into constituent pieces. So the lead and one of the oxygen atoms, it breaks apart in such a way that that sticks together. And then the remaining carbon with the two oxygens that were left over is what sticks over here. So is it balanced? Lead and lead, one of each, one carbon. There's three oxygens here, 1, 2, 3 oxygens. So this is actually also initially a balanced chemical reaction. There's nothing to balance, it's already balanced. It's starting with something complex, breaks into 2 or more. Say I have A plus B, but decomposition can be broken into 3 or 4 or 5 products as well. Anytime it breaks into more pieces, starting with one compound, we call it a decomposition reaction. All right, so let's take a look at the next reaction. Let's take a look at potassium chlorate, ClO3, and that will be a solid. And that reacts and breaks down into something called KCl, potassium chloride, and then O2 gas. First of all, does this look like a decomposition reaction? Well, you start with something complex and it breaks apart. In this case, the potassium and the chlorine stay together as a unit and the oxygen is broken apart here. But you can see it's not balanced because one potassium, one chlorine, 3 oxygens and only 2 oxygens. So this is not a balanced chemical reaction. So let's write down this again without the states of matter. And let's balance it. So KCl, O2. When oxygen is left by itself, it's generally not going to be O3. O3 is a molecule called ozone. It is something that we find in the atmosphere, but it's not the most stable form of oxygen. Usually oxygen will exist as O2 unless there's something else going on. So that's why it doesn't just split off as O3. Ozone is not quite as stable as O2 gas is. That's what we breathe every day. So let's balance this. 1 potassium, 1 potassium, 1 chlorine, 1 chlorine. 3 oxygens, 2 oxygens. Now, how can I put a coefficient in front of this to make a 3? Well, you need to embrace fractions. As I've been telling you, when you balance your reactions, don't be scared of fractions, because otherwise you have to find the whole numbers that make it work. But I can tell you that if I'm trying to have 3 oxygens over here, the way to do it is to put the fraction 3 halves. Because if I take 3 halves and multiply by 2, the 2's will cancel, and this actually is 3 oxygen atoms, right? Remember, 3 halves multiplied by 2 over 1, this multiplied by this 2, gives you an answer of 3. So this, when you multiply it, is 3 oxygen atoms to balance this. However, we don't like fractions in our final answer, so what we're going to do is multiply by 2 to clear the denominator. All right, so what we're going to do when we do this is we'll multiply this by 2, so 2 KClO3. Multiply this by 2. Every term has to be multiplied. 2 potassium chloride. And then this has to be multiplied by 2, so the 2's cancel, giving you 3O2. All right, now let's see if this is, in fact, balanced. Of course, you could be more correct by putting the states of matter back in. I'm not going to do that for every problem here. 2 potassiums, that's good. 2 chlorines, that's good. 2 times 3 is 6 oxygens. 3 times 2 is 6 oxygens, that's correct. So if you are scared of fractions and you don't do this, then what you would have to do in the first step is figure out what coefficients, whole coefficients, will balance the oxygens. And you'll have to do it 2 at a time. Multiply this by 2 and multiply this by 3. But a more bulletproof way of doing it is just balancing the oxygen with a fraction and then clearing the fraction away. It'll save a lot of time. So far we have had combination reactions, 2 species or compounds coming together forming a single product. And we've had decomposition, where we have a single, more complex product breaking down into multiple, or I should say reactant, breaking down into multiple products. And so now what we have to do is talk about our third type of reaction, which we've hinted about it up until this point. It's called a combustion reaction. Now, in this case, I'm not going to do, like an A plus B or whatever. I'm just going to talk about it, what it means. I think a lot of us know generally what combustion is, but we need to talk more about the chemical and the chemistry formal definition of combustion. First of all, combustion must involve oxygen. If it doesn't involve oxygen, it's not combustion. So it has to, one of the reactants essentially has to be O2 gas or O2 of some kind, right? Secondly, combustion usually is a more rapid reaction that involves heat, it involves light, and the products of the combustion reaction are almost always CO2 plus H2O. We're going to talk more about why CO2 and H2O later. We're going to talk a lot more about why those are almost always the products. Well, it just turns out that water, H2O, is a very stable compound. And CO2 is also a very stable compound. Very, very stable means whenever things burn, they like to go into the most stable configuration. And CO2 and H2O are the very, very, I don't want to say the most stable, but they're very, very stable configurations of oxygen, hydrogen, and carbon, okay? Now, before I write any reactions down, I want to talk a little bit about what's happening in your body. In your body, you are burning fuel. You eat the fuel, you drink the water, right? And in your cells, there's not really a combustion reaction happening, but the final product of the reaction is CO2. We breathe it out. And there's also water involved as well, CO2 and H2O. But the difference is in your body, it's not considered combustion because it's not a single step rapid reaction that involves lots of heat and light in your body. In your body, there is a whole process of taking the food with many, many intermediate chemical reactions. In other words, the burning, quote unquote, happens very slowly in your body over many, many intermediate reactions. When you talk about biochemistry, you learn about all the intermediate reactions that are happening in the body from step 1, which is food going in, step 2, 3, 4, 5, 6, 7, 8, all the intermediate reactions. And at the end of the day, you get you get carbon dioxide, we breathe it out, and water as well. We produce water as well, and you know how you get rid of water from your body, okay? So, but we don't call that combustion. We don't call it combustion, even though it sort of is, because combustion in chemistry usually means you combine with oxygen rapidly to produce a product, and it has heat and light. That is what we usually are talking about combustion. So all reactions that involve oxygen, they're not all combustion, is what I'm trying to say. For it to be combustion, it must involve oxygen, and it must also involve heat, light, and usually it occurs rapidly, at a rapid rate. Okay, so let's write down what a typical combustion reaction is. Now, I'm gonna write this down in balanced form because we've done it so many times. What about H2 as a gas? Add it and react it with O2, which is a gas. What do you get? Well, you all know that you get H2O. And you all know that this is not a balanced reaction because you have two O2s and only one right there. How do you balance it? You need to put a 2 right here to make 2 O2s, and that unbalances the hydrogen. So to fix that, we need a 2 right here. This is a balanced reaction. 4 hydrogens, 2 oxygens, 2 oxygens. Gas, gas, gas. This is a combustion reaction. And you know that it occurs rapidly because a lot of rocket fuel actually is hydrogen. And so it is very, very, very energetic reaction, produces water and lots of heat and lots of light and very rapid. That's a combustion reaction, right? Not everything that combines with oxygen is combustion. So it has to have those other qualifiers we talked about. All right, now let me write one more down underneath it, and then we'll go back and give some more examples of the other types. This is one that's very simple to understand because we've talked about it already so much. Let's talk about burning another type of fuel. What about the fuel C3H8? This is a gas. This is called propane gas. And I know we haven't gotten very deep into the what we call organic chemistry, but we did an introductory section on it before. If you remember, when it's 1 carbon, it's called, the prefix is methyl. When it's 2 carbons, the prefix is ethyl. And when it has 3 carbons, the prefix is propyl. And then 4 is butyl. And then it goes on up from there, right? And this is not an organic chemistry class, but we did learn those prefixes in the past. That's why this is propane, because it has 3 carbons. Methyl, ethyl, propyl. So propane, right? That's what we have here. Notice there is a lot of hydrogen wrapped up in this compound with the carbon. So you already know that carbon is flammable. It will combine with oxygen, and you definitely know that hydrogen is flammable because we know it combines with oxygen. So this is a great fuel. It is a molecule that contains lots of things that like to combine with oxygen. The carbon likes to combine with oxygen. The hydrogen most certainly likes to combine with the oxygen. It's chemically bound up together in a molecule we call propane. Now, if we add this together with oxygen gas, what do you think is going to happen? Well, you don't really need to figure out how it's going to work and all this, because in general, if it's real combustion, that means it happens energetically, very rapidly, involving heat and light. The products are almost always CO2 as gas and H2O as gas. Almost always. Now, sometimes you can have situations where it's not carbon dioxide. You might get carbon monoxide, right? And there's other things that can happen, but we're going to save that for later when we talk in more detail about combustion, because we are just scratching the surface here. We're going to talk more about combustion a whole lot more later. And, we can there are more rules of thumb to predict what's going to happen. But in general, when things combust completely, when there's a lot of oxygen available to freely combine with everything that's burning, generally you make CO2 and H2O almost all the time. So on an exam or a test, if it says, some kind of carbon compound is burning, right? Some kind of, we call it a hydrocarbon, where there's hydrogen and carbon and it's burning. The result of it is going to be CO2 and H2O, because if we have an abundance of oxygen and all of this, then complete combustion, those are the most stable products that can form, and they're going to form, with great abundance. There could be some tiny amounts of carbon monoxide present, but in general, CO2 and H2O. Now, is this a balanced chemical reaction? No. Why? Because there's 3 carbons here and there's only 1 here. So we know immediately it's unbalanced. So let's write down the chemical reaction again. C3H8, that's our propane. O2 gas yields CO2, H2O. Now, just because it's a combustion reaction it doesn't really change the rules of the game. We still follow the same rules of balancing reactions that we have always said. We try to keep the oxygens for the last part of the balancing process and the hydrogens for the end also, if we can. And then other than that, we just look for the more complicated molecules in the beginning to start trying to balance, and we just go left to right, and that's more or less the process. So we're going to leave the oxygen for the end. We're going to leave the hydrogen for the end. So we go back and we say, well, I got to deal with the carbon. 3 carbons and only one of them here. How do I fix that? I put a 3 here. I've balanced the carbons. So let me rewrite this. C3H8O2, 3CO2, and then we have our water, H2O. So 3 carbons, 3 carbons, what's left? I want to leave the oxygens for the end. Why? Well, in general, you want to do that, but the reason is because the oxygen is off by itself here. And so I want to save it for the end because I know I can always balance the oxygen easily by just putting a number in front of this, and it will not affect anything else in the reaction. You see, if you start changing coefficients of things that have multiple elements in there, then it's going to have a ripple effect and it can undo some of the balancing you've already done. But if I save oxygen for the end, I know I can balance it because this is isolated. So if I've already balanced the carbon and I'm not going to touch this, I need to move on to the hydrogen. There are 8 hydrogens. Hydrogen is here. I balance it by putting a 4 right here. And I'm going to recopy the thing again. C3H8O2 yields 3CO2, 4 H2O. All right, 3 carbons, 3 carbons, 8 hydrogens, 8 hydrogens. Okay, how many oxygens? I have 2 here. However, over here I have 6, 3 times 2 is 6, and then I have 4 more. So I actually have 10 of them, 10 oxygen atoms on the right. I only have one position here to fix it. How do I make 10? I put a 5 right here. So I'll just put a 5 right here. And so the answer to this is C3H8 plus 5O2 yields 3CO2 plus 4H2O. Now to be more correct, you would put right here gas, 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 and gas, and you put the states of matter here. I'm not going to write it for every problem because it'll clutter up our board, but you should put the states of matter in place. Now what does this mean? It means that if you take a single propane molecule that has 3 carbons and 8 hydrogens in that single molecule that's bound together, then you need to react that single molecule with 5 molecules of oxygen. Not 1, not 2, not 3, not 4, but 5 molecules. Remember, each molecule is O2, 2 oxygens. So you need 5 of these to react with one of these molecules. And the end result is you will have 3 molecules of carbon dioxide and 4 molecules of water, and that will account for all of the atoms in the chemical reaction. So the ratio that these things are combining at is 1 part of this molecule to 5 parts of this molecule to 3 parts of this molecule to 4 parts of this molecule. So at this point, we have given 2 examples of combustion reaction. We've given 2 examples of decomposition reaction, and we've given 2 examples of combination reaction. So what I want to do now to finish out the lesson is just to give 1 or 2 more examples of each class. Now that you have a flavor of what they all are, let's just go and do a couple more. It's not going to take long. I just want you to have a little more exposure to a couple more additional examples of each type. All right, so what would be another example of a combination reaction? Another example of a combination reaction. I'm trying to find out one I have not written yet. What about calcium oxide as a solid combining with water? Let's say it's in liquid form. And the result of that is going to be calcium hydroxide. OH is hydroxide, and so it's CaOA2 and OH2, sorry, and that's an aqueous solution there. All right, first of all, is this a combination reaction? Well, you have 2 species, 2 different reactants, and they combine together to form a single product. All of the atoms that are here in both of these reactants are now present in the final product, and there's only one final product, so it's a combination reaction. Is this balanced? 1 calcium, 1 calcium, 1 oxygen, but there's another one here, so there's actually 2 oxygens, and then over here, the OH, the hydroxide ion, there's a 2 there, so there's actually 2 oxygens, so that balances. 2 hydrogens, and for the same reason you have 2 hydrogens. So actually this is already balanced. There's nothing to do any further. It's a balanced chemical reaction, and we know that it is a combination reaction. All right, let's do one more of this type. And the last one we're going to do is going to be this. Nitrogen, N2 as a gas. And we're going to add to that hydrogen, H2 as a gas. And the result of that is going to be NH3 which is a gas. All right? So is this, first of all, a combination reaction? Two different reactants combined together to form a single product. It looks like a combination reaction to me. Is it balanced? Well, no, because we have two nitrogens and only one here. So let's rewrite it into H2, and then we have NH3. So again, we want to leave hydrogen for the end. In general, we like to do that, but the other reason is it's by itself. We know we can always balance the hydrogen because it's isolated. And so we have two nitrogens and only one here. How do we fix that? We put a 2 in front. Let's rewrite what we have. We have N2, we have H2, and then we have 2 NH3. Okay? And so we have two nitrogens. Here we have 6 hydrogens. How do we make 6 here? We need to put a 3 here. 3 times 2 is 6 hydrogens, and that's a balanced chemical reaction. So N2 plus 3H2 yields 2 NH3. And to be more correct, you would put gas, gas, and gas down, but I'm not going to write that for every time here. I want to point out something, that the first 2 examples of these combination reactions, they're all clearly combination reactions because 2 things are coming together to form a single product. But in the first 2 reactions, they were also combustion reactions because they were combining with oxygen, and heat and light, you don't really know that ahead of time, but I'm telling you, heat and light are involved in these, and the products are formed. And so because heat and light combining with oxygen, they're also combustion reactions. So these first 2 were combination reactions, but they were also combustion reactions. These last 2 are combination reactions, but they are not combustion reactions because even though there's an oxygen in the water and there's an oxygen here, this is not combining with oxygen. When we say combining something with oxygen, we mean one of the reactants has to be O2 gas. That basically has to be true in order for it to be combustion. So this is not combustion, but it is combination. This is not combustion, but it is combination. Okay, we're now done with combination reactions. So let's move along to the decomposition reaction and just give a few more additional examples. They're not going to be difficult or anything. I just want to give you a little more practice with it. What if you have copper hydroxide, CuOH, 2. The OH is the hydroxide ion. Sorry about this. The 2 has to be out here. There's 2 of these hydroxide ions. And that is a solid. And that decomposes into copper oxide as a solid and H2O, water, which we can say is a gas here. So is this a decomposition reaction? Yes, because it's a single complex reactant which breaks apart into 2 or more products. Right? Now notice, it doesn't just like split off and you have copper by itself and then the OH by itself. It's not so simple, but you can see that the copper and one of these oxygens are kind of split off together, and then the other oxygen combining with the hydrogen that's left over makes the H2O that we have there. So it is the constituent parts breaking into simpler pieces. Now, is this a balanced chemical reaction? Well, we have one copper, and so that's balanced. For oxygens, we have 2 oxygens, and over here we have 1, and there's the second oxygen, so that's balanced. We have 2 hydrogens and 2 hydrogens. So actually, this one is already balanced without doing any further work. So we're going to circle that. All right, let me give you another example of a decomposition reaction. What about calcium, Ca, and then CO3 as a solid? And then we're going to draw an arrow, and I'm going to put a triangle on top and explain what the triangle means in a minute. And that yields calcium oxide as a solid and CO2, which is a gas. First of all, is this a decomposition reaction? You start with something more complex, and it breaks apart into simpler products. That is a decomposition reaction. Is this reaction balanced? 1 calcium, 1 calcium, 1 carbon, 1 carbon, 3 oxygens. You have 2 here. The third one is here. So this is also a balanced chemical reaction. We don't have to do anything to it, so it's already balanced. It's done. And the last part of it is, what's this triangle for? We're going to get into this a lot more later. But when you see a triangle in chemistry, it almost always means heat is involved. So to make this reaction go, you have to add heat. And in fact, we didn't talk about this for some of the other reactions. They quite often require a little bit of heat in order to at least get started. But some reactions only require heat to get started, like starting a fire, and then the heat that the fire generates is enough energy to keep the reaction perpetuating, okay? And then other reactions require heat the entire time for the reaction heat to be applied for the entire time for it to continue going. So this triangle means that we need to keep applying heat some sort of way to get this thing to continue to decompose and to continue to form these products. The triangle over the arrow means need to be adding heat in order for this to happen. Now later on in chemistry, we're going to talk a lot more about heat. We're going to be able to quantify heat. We're going to treat heat as an ingredient in the reaction like anything else, and we're going to write down numbers to represent heat. And so we're going to get very, very mathematical with heat later on. For now, I'm just saying, hey, there's some heat. But just know later on, we're going to write down exactly how much heat was involved in this reaction. Where does it go? How do we write it down? Because heat is very important in chemistry. All right. And we have one more example. Our final example is actually really interesting. Take a look at this molecule. Whoops, already messed up. N3. So this is sodium and 3 nitrogen atoms as a solid. Decomposes, or can decompose, into sodium as a solid and into gas. Now this is a very interesting real-life application. I'll talk about it in just a minute. First of all, is this a decomposition reaction? Single complex product breaking down into simpler pieces? Yes, it's decomposition. Is it balanced? 1 sodium, 3 nitrogens. That is not balanced because it's 2 nitrogens. So we rewrite it. Na(N3) yields Na plus N2. So we have 3 nitrogens on this side. How do we write something down to get 3 nitrogens on this side? We need to use fractions. So we make it 3 halves because we multiply by 2. The 2's cancel. This is 3 nitrogen atoms on the right to balance what we have here. But we don't like to have fractions in our final answer. This is balanced because we have 1 sodium, 3 nitrogens, 3 nitrogens. We now have to multiply by 2 in order to clear the denominator of the fraction out. So we multiply by 2, 2Na(N3), and that is a solid, and that decomposes, and we multiply every term by 2. So this is 2 sodium as a solid, and then this multiplies by 2, which cancels, and so you have only the 3 N2, and this is a gas. So we have 2 Na(N3) yields 2 Na as a solid plus 3 N2, which is a gas. So this is the final answer for this decomposition reaction. And this is actually really interesting because this is involved in how the airbags deploy in a car. All right. So there's the solid substance, Na(N3), and when you, it's more complicated in how it's engineered in a car, okay? But when you get the reaction going, either through a heat source or something like this, when it detects a crash, then what happens is very, very, very rapidly, some sodium is produced and some nitrogen gas is produced. And the gas that's produced occurs very, very rapidly, and it kind of explodes and inflates the airbag. That's where the gas is coming from. A lot of people think there's a gas canister somewhere, and then the gas canister just fills the airbag. No, because an airbag has to deploy much, much faster than a valve can open, right? So this chemical reaction is almost like an explosion, and this nitrogen gas, which is non-toxic, we breathe nitrogen every day, inflates the airbag. Now, it's more complicated than this, of course, in real life, because the other product is sodium. If you remember, sodium from the periodic table is very reactive. It reacts with water very, very violently. And so if you breathe in sodium, the moisture in your face, I mean, you would have a nasty burn just from the sodium. So in reality, when they make real airbags, there are other chemicals involved in this to make the explosion and the sodium harmless to a person. But the core reaction that inflates the airbag is written down right here. So 2 of these guys, these compounds here, yielding 2 parts sodium and then 3 parts nitrogen molecules. All right, so we have the decomposition reaction. That's all I'm going to write down for those. And we've already done 2 of the combustion reactions, and I want to do one more just so we can kind of like wet our feet with something slightly more complex. Let's write down something called ethanol, C2H5OH. That's a liquid. So this is ethanol. Remember I told you a minute ago, I said in organic chemistry, we talked about this. 1 carbon means methyl group. 2 carbons is ethyl. 3 of them is propyl. And then it goes on from there. Well, this has 2 carbons, so this is ethyl. And the OH here is the alcohol group that turns it into an alcohol, and so it's ethanol. Ethyl means 2 carbons. Alcohol means, or ethyl alcohol, ethanol, okay? So that's what we have there as far as the naming goes, ethanol. And if we want to burn this stuff, we're going to have to combine it with oxygen gas. And what's it going to yield? Well, I'm telling you the secret. You basically know it's always going to produce CO2 plus H2O. If there's ample oxygen, that's what it's going to produce. If there's not enough oxygen available, it'll probably produce carbon monoxide instead. But if there's ample oxygen here to react with everything, it's going to predominantly produce CO2 and H2O. That's pretty much always going to be what you have. All right? So is this balanced? Well, we know it's not because we have 2 carbons here and only 1 here, and that's enough for us to just rewrite the thing and balance it. So C2H5OH plus oxygen gas yields CO2, H2O. We already know from experience we're going to leave the oxygen for the end, we're going to leave the hydrogens for the end, and the only thing left in here is basically the carbon. And so we're going to start working with carbon. There's 2 of them here and only 1 here, so we fix that by writing down the 2 right there. So we're going to write it down again. C2H5OH plus O2 yields 2 CO2 and H2O. Now, we've balanced the carbons. The oxygen we definitely want to leave for the end. How about hydrogen? 5 of them here. 1 more means 6 hydrogens on the left. 6 hydrogens on the left. On the right, we only have 2. How do we make 6 over here? We're going to put a 3 right here. 3 times 2 is 6 hydrogens to balance the 6 hydrogens right here. And so we're done with that. Now let's rewrite it again and see if we are balanced. C2H5OH, O2 gas, 2 CO2, 3 H2O. All right, so we have 2 carbons, 6 hydrogens, 6 hydrogens. Only 2 oxygens. Over here we have 3 from here, and then we have 4 from here. So 2 times 2 is 4. So there's a total of 7 oxygens over there. So how can we fix it and make 7 over here? Well, we have 1. We need 6 more, so we're just going to change this into a 3. That means 6 oxygens. 1 more is 7 oxygens. To balance, 4 plus 3 is 7 on the right-hand side. So carbon is balanced, hydrogen is balanced, and the oxygen is also balanced. So C2H5OH plus 3O2 yields 2 CO2 plus 3 H2O. And that's the balanced reaction. Now, we would typically write the states of matter in place and make it a little more prettier and more complete, but I'm not going to write that for every problem here. Now, one thing you might be interested in is, or to, as an aside, I'll just tell you, because we get into it a lot more later, but I'll just tell you in passing. This guy, this ethanol here, is written, in this case, as C2H5OH. Why don't we just write it as C2H6? Why can't we just put the H over here and make it H6 and then O? Or put the O in the middle and make H6 over here? All we generally try to do with these molecular, we write down the molecule there, is we're just representing the number of atoms. So why don't we lump all the hydrogens together and make it H6 and make it C2H6O or something like that? Well, the answer is you could do that. But the reason we write it like this is because later on when we get into organic chemistry, we're going to find out that we try to represent as much of the structure in the way we write it down as we can. And what this implies is that the OH is hanging out together by itself. It's kind of like that's what makes the alcohol an alcohol. So we don't want to lump the hydrogens together because the OH is hanging out as its own group, and that's what makes it an alcohol. When you actually look at the molecular model of this, which I don't want to do now, we will do it sometime in the future, you're going to find out that that OH is hanging off one end of the molecule by itself. And these other 5 hydrogens are sprinkled in 3-dimensional space all the way around everything else. So these 5 are kind of like spread out, and the OH is what makes this molecule unique. It's what makes it a distinctive classification in terms of it being an alcohol. And you kind of lose that if you combine the hydrogen in here and make it H6, then you cannot immediately see that it's an alcohol. But when you see OH by itself, then you pretty much know it's an alcohol of some kind, and that kind of thing is important for organic chemistry. So we have conquered combination reactions, decomposition reactions, and combustion reactions. And I'll just point out one more time, since we've done the combustion here, notice that this combustion is happening in one step. CO2 and H2O are forming. It's usually involving heat, light, and it's a rapid chemical reaction. When you eat food in your body, the products are still CO2 and H2O. However, it doesn't happen in one step, otherwise you just catch on fire. It happens through many, many intermediate steps, which you learn about when you study biochemistry. All of that is happening inside of your cells. And so the progression from the complex food molecule to the simple CO2 and H2O is still happening, and all of the heat that is released and the energy that is released and the burning of campfire or some kind of, like, in this case, ethanol, you can see all of the energy that's coming out of it. The energy is coming from the chemical bonds in the alcohol, or the chemical bonds, in this case, it was propane, right? And so the energy is not coming from nowhere. It's coming from what the fuel contained in terms of the bonds inside of the reactant, inside of the fuel. All of that energy is going into your body. That's the energy that you use to walk around, to go about your day. However, it cannot be all released like that because you just burn up. So in your body, the same sort of end state, the CO2 and H2O, is kind of like reached, instead of in one step, going through a series of intermediate reactions, which releases the heat slowly. It releases the energy slowly into your body, into a lot of intermediate products. And that is basically the idea. That I just found that when I learned that a long time ago, I was just fascinated by that. That essentially you're burning your food, but you're doing it in a slow and controlled way so that we can use the energy instead of like a campfire, which is gone immediately, and we can't really harness it so well because it just goes up, the heat, the light comes out, and it's done. So, combination reactions, two or more things coming together to form a single product. Decomposition reactions, single reactant breaking apart into two or more simpler products. Combustion, something combining with oxygen, O2 gas usually, forming products, usually CO2 and H2O, that produce heat, light, and almost always a flame is involved as well. So I'd like you to go through this a couple of times and make sure you understand these three different kinds of reactions. Follow me on to the next lesson. We'll continue talking and getting practice with combination, decomposition, and combustion reactions.